So I think I'm not late and I can start right away. Do you need some sort of introduction and some other formalities to begin with?
Yes, sir.
Okay, please go on. Yeah, thank you.
So, very good morning to all the faculty members, our eminent speaker, Professor Prashant K, and dear participants. I welcome you all in session 1 on day 6 of AICTE ISTE 1 week online refresher program, which is on artificial intelligence and cooperative Noma 5G network. I would like to welcome our eminent speaker, Professor Prashant K, Associate Professor for Nazarbayev University, Astana, Kazakhstan. It's my pleasure to introduce him. Professor Prashant K. earned PhD degree and a postdoctoral fellowship from the University of Auckland, New Zealand. Earlier, he had obtained MTech from IIT India, securing the first position in all the disciplines, and BTech from MNIT, Allahabad, India. Presently, Professor Jamwal is working as an associate professor at the School of Engineering and Design Sciences, Nazarbayev University, Astana, Kazakhstan. He is actively pursuing research in artificial intelligence, multi-objective evolutionary optimization, mechatronic systems, biomedical robotics, and fuzzy mathematics. He is applying his research in the development of medical robots for relievation of and surgical application, besides the development of improved algorithms for cancer data analytics. He has more than 25 years of teaching and research experience and has published many research articles in reputed international journals and conferences. Professor Prashant has won many awards such as Best Paper Award in conferences, Best Digital Solution Award for his medical robots, Asian University Alliance, AUA, Scholar Award, etc. And recently, United Nations acknowledged one of his robotic projects as one of the top 20 innovative projects in the world. He is working as editor for the International Journal of Biomechatronics and Biorobotics and as a reviewer to quite a few international journals and conferences of repute. Professor Jamwal led many government-funded research projects also. Welcome you, sir. And now I would like to invite Professor Prashant K. Jamwal to deliver his talk on artificial intelligence in healthcare. Welcome you, sir.
So kindly unmute yourself.
I'm sorry, I was muted. And thank you so much, Anila, for a great introduction. I feel bit, I'm happy for this, introduction and all that. Yeah, but the goal is to continuously keep learning newer things and keep moving. Though these are the achievements that we always keep as a record and would like to as a motivation for us to keep moving. But definitely there's much more to achieve and there's much more to learn. Thank you very much for inviting me to this conference. I have been to this conference previously as well, and I've always enjoyed, participating in such kind of workshops where we have learners who are very keen, not like other conferences where people
Sir, you are not audible.
Yeah, I'm sorry for this internet problem. I don't know where this problem was, but I hope I'm audible now.
Yes, sir. Now you are audible.
Okay. So, yeah, let me share my desktop. and this is where I wanted to start actually. So can you see my full screen view?
Yes, sir. It's visible.
Okay, great. So I'll start with a brief introduction of mine. As Anila rightly said that I did graduated from IIT Roorkee and then did my PhD from University of Auckland. Both these institutions are quite old, as you can see. The institution that came into being in 19th century. But yeah, for now, I'm teaching in a very relatively new university, which is less than 10 years old, Nazarbayev University. It is a very famous university in Kazakhstan and in Central Asia. In less than 10 years, we have achieved research excellence and have become research flagship university in the entirety of Central Asia and Russia. So today's agenda, because the topic suggests about artificial intelligence and machine learning. So what I'll try, because we have very honest seekers here. So I'll take an overview of the machine learning and artificial intelligence approaches, and then I'll start talking about their applications in the healthcare. Now, the thing is, we started to talk about AI and machine learning very recently, but the fields, the technologies, the algorithms, they were existing for a very long time. I remember my tenure in IIT Roorkee back in 2000. So we used to talk about AI and machine learning in those days, which is like 20 years back in time. And there are books available for more than 30 years. So there's nothing new. What is new is basically the capability of the computing. So as the computing capabilities has increased, so the applications of AI and machine learning have also increased. But still, as I say, that machine learning and AI technologies were existing for a long time. But definitely in the recent time, we have seen surge of new applications, new innovations, newer algorithms and applications. So definitely everything is included in this presentation. Because we have sufficient time, so I was thinking of going slow and trying to cover the basics of these technologies. So let's begin with the data. When we talk about machine learning or artificial intelligence, be it in communication, be it in transport or healthcare, whatever sector we talk about, the fundamental entity of all these machine learning and AI is the data that we work on. So we need to understand how and what kind of this data is. So basically, to collect the data, we use a lot of sensors, and with increase in number of sensors, so the data and data types are also increasing, and that's something is causing the big data. If we talk about the sensing and data collection, then basically we are talking about Industry 4.0, which is not today's subject, so I'll not talk about that. But the data types is important to know for this particular presentation. So the data could be, simple textual data like alphanumeric data that we always, deal with. The data could be images. When we talk about medical sensing and medical applications of AI and machine learning, we normally work with image data, and that comes from scans and various other, X-rays and other kinds of pictures. The data could also be simulations, or it could be graphs, So, but that's not then. The data could also be in terms of, voice signal or the audio signal. So we collect all these kinds of data dealing with when we, have applications in the medical field, in the healthcare. Apart from all these textual image simulations and sound, we also can have data in the form of videos. I mean, of course, videos are nothing more than continuous frames of continuous flow of frames or continuous flow of images, of course. But still, the data in terms of videos is again very important, held slightly differently. Now, all this data has to be converted. As you can see, all these arrows they would suggest data we normally convert to a particular mode or to a particular form that the computer can understand. So mostly all these data we try, first thing is we need to convert them to a digital data, and which is of course normally a binary data. Now once we have converted data to the language the computer can understand, next is what we are trying to do with the data. So there basically we try to learn the pattern of the data and then try to infer or maybe predict or prognose something that may happen in future, right? So the entire thing, understanding the data pattern, modeling it, and then with the help of the model, the ability to predict it for the future course, the entire process is termed as data analytics. Data analysis is one part, but when we have a modeling and predictive capabilities put into this analysis, the entire thing becomes data analytics. Now, once again, there can be three kinds of, the entire data analytics, it has three kinds of data analysis. The first kind of data analysis would tell us what is happening, and if we continue with the same system without changing, without intervention, what will happen in future? But at the same time, we can also perform a data analysis that can help us tell that what should be done, what changes need to be done in order to make some corrections for the future predictions. So these three kinds of data analysis that I'm talking about are termed as descriptive, predictive, and prescriptive analysis. So the descriptive analysis will tell us what's happening, what's going on in the system. The predictive analysis tells us, continuing with the same system, what will happen after some time in future, maybe 1 year, 5 year, 10 year, whatever. And the prescriptive analysis, on the other hand, would tell us that if you want a different course of, if your goals are, let's say after 5 years, continuing with the same system, you reach to a certain point, but you want this point to be changed. You want to change the goals, or you want higher goals to achieve. So for that, to achieve higher goals, what changes that you need to do in the current system would be advised by this prescriptive analysis, which is the third kind of analysis I was talking about. Now, how do we carry out these kind of analysis? So basically, there's a process of data analytics and starts right from the identification. So we need to know what information is important, and then we try to collect it. We don't collect the information which is not important, of course. And so that's the process called identification. In order to, for instance, in order to find out what's happening in my musculoskeletal system or what's happening in my brain system. So there are different kinds of sensors, and different kinds of sensors would give me different kinds of information. So this identification of right kind of data is very important. And then we try to collect this data through sensors. Collecting data through sensors would mean that the data type, the sensor would give me some sort of signal which may not be readable for the computer. So the signal has to be converted in the language of the computer. For instance, most of the sensors, they would give me output in terms of voltage or currents. So that voltage or current from the sensors has to be further processed. You know, the data in terms of voltage that I'm getting from the signal, that has to be calibrated with the physical variable that I want to understand. I mean, for instance, if it's a temperature sensor, right? So the temperature sensor giving me voltage in terms of current or volts has to be converted to a particular temperature scale. So some sort of calibration is required. And then apart from the calibration, we also need sometimes amplification, because the signal is very low, because mostly we deal with the low voltage electricity there. So all this comes under the head of processing. And then once we have converted the data, and the data is now, we are able to read the data, then the problem comes is that how big is our signal? I mean, are we able to read the signal correctly, or if the signal has a lot of noise? It does happen normally when we take, you know, for instance, biosensors. When we deal with the biosensors, such as electromyograph or ECG, electroencephalograph, ENG, for instance. So these are the biosensors. They're very useful, and they're very crucial for getting, you know, human body, information about human body, without you know, I mean, in vitro, right? Now, for such kind of information to get from human body, we need these biosensors, and then biosensors, they give us signal, as well as they'll give us some noise signal. So it's like just not the noise. Basically, you get some cross information. For instance, if you're talking about EMG, now the signal that I'm talking about will have a lot of crosstalk. So I have to filter the signal and identify my signal amongst all existing signals and noises. So to clean the signal, to clean the, you know, sensor output, in terms of to extract the right signal to read and reject the noises and the crosstalks, is a very difficult process, of course. But then those who have studied about signal processing, they would understand what I'm talking about. And so once the output from the sensors, the data has been cleaned, now we've got a set of data that we can actually define in terms of inputs and outputs, and that paves our way to further modeling and further communicating the data analytics. So all this process requires two stages, basically. One stage is the classification, and the other stage is regression. At the classification stage, we try to segregate the data in terms of inputs and the outputs. Right? We should know what data we want as an output, what data we need to extract a particular information. You know, from the data there could be many kinds of information that you can extract. But once you know what kind of information you're interested in, then probably you can work with the data, and then you can select what should be your output data. Now, sometimes it is easy to, you know, for instance, if I'm reading a cancer slide, if I'm reading a PET scan or a CT scan, and I know the points of interest, right? And so I can easily define them, and I know what are my regions of interest, and I can define them as an output. But sometimes we are not sure. We're not sure about what are the output data, and so the entire data has to be learned in such a way so that we can find out, we can divide the data in terms of inputs and outputs. And so this becomes sometimes very tricky. The classification is very tricky sometimes. So the instances where I know what are the inputs and outputs, and I know this kind of classification, it's easy. So this is called supervised learning. But the cases where we do not know what is the important information that we can extract from the given data. And so we cannot classify them with the known information. Then this kind of learning is known as unsupervised learning. And then there are ways to do it, of course. But basically, this is the first stage in our data analytics, be it with the support of machine learning algorithms or artificial intelligence. The first stage in all kinds of data analytics would be the classification, where we try to classify the data available in terms of what goes in and what comes out. Now, once we know what are the inputs and outputs from the data set, then it becomes easy for one to create a model. Now, creating a model, it looks quite scientific, but it's not a rocket science. It could be as simple as, modeling the data, fitting the best curve, or maybe sometimes could be just, the mapping between inputs and output could be a straight line. So basically, when we're talking about the regression or modeling or whatever, we need to come up with a relation between inputs and the outputs. Now, as I was telling, this input-output relationship could be a straight line, could be a curvilinear, or it could be a surface, or it could be hypersurface sometimes. So depending on what kind of relationship exists between input and output, there are various kinds of regression available. And so I've listed here, as you can see, there could be a linear regression, it could be polynomial, we could use support vector regression. We also work with decision tree regression. These days we have started to work with random forest and bridge and lasso regression as well. And when you talk about, for instance, this neural network, that we normally work with the logistic regression. Different graphs, they would show how different kind of regressions are identified. But going once again, as I was telling you, that the regression modeling, it's not all that difficult. It could be as simple as drawing a straight line. If you recollect from your high school mathematics and try and figure out that straight line equation, So okay, wait. I think I went further. Yeah. So the regression I was telling, that could be as simple as drawing a straight line. So if you recall, that equation of the straight line was y equals to m times x plus c, right? Now this y and x, they can be denoted as the output and the input. So x could be defined as a vector of inputs, and y could be defined as the output vector. And the entire equation of straight line, it has two kinds of constants, which are m and c. So the constant m would denote the slope of the line, whereas the constant c is used for the offset that it has from the origin. Now, once we have this m and c available, you can give any value for x and you would be getting a value for y automatically, and the regression model is ready for you. So the entire exercise of finding this m and c for between the input and output data is all called the regression. Now this is a simplest example, but then as the data, as the relationship between the inputs and output gets complicated, so the regression also gets complicated and cumbersome. So as I was telling before, that the supervised and the unsupervised learning algorithms, they have to deal with different kinds of data set. Now, for the data where we do not know what are the inputs and outputs, and we cannot do any classification, there we would use these unsupervised machine learning algorithms. So Once again, there's a number of different algorithms that you can use, like k-means clustering, and then this stochastic neighbor embedding. We use PCA, principal component analysis. There's one very important algorithm that we termed as association rule that we use. So there we try to do some sort of embedding and try to find the data which is related and data which is not related. And this is how we try to segregate and do the classification. But for the case where we already have the information on the inputs and outputs, we use supervised machine learning algorithm and we can easily venture into the regression. Sometimes people do ask about the difference between artificial intelligence and machine learning. So here's a quick visit on AI and machine learning comparison. So in the machine learning, in the machine learning algorithms, they would learn the relationship between inputs and outputs and then works pretty well. Sometimes even better than the artificial intelligence algorithms. They can give us very good accuracies, and at times when a single machine learning algorithm is not working, so we can actually go for an ensemble of different machine learning algorithms, put them together, and then get very high accuracies, and so that's fun. But the problem with the machine learning algorithm is that the moment you have your system is changing slightly, or if your system is dynamic, in that case the machine learning algorithm will have to be trained always afresh. But with the artificial intelligence, this is not the case. The AI algorithms would, while they learn the relationship between the inputs and outputs, they also try to learn what are the inputs and outputs. So what I'm saying is, for instance, here if you can see this this figure on the right hand side, this is a screenshot of a game that we used to play on our mobiles and screens. It's called Minefields game. So one has to enter from one point and exit from another point, keeping away from these mines. Because if you enter into, if you get connected, or if you cross through these minefields, you'll be blasted. So one has to traverse through without getting into the minefields. That's kind of the objective of the game, and we normally try to play with. Now we can use machine learning algorithms to learn this minefield and find out the best optimal way from entry to exit without getting into the minefields. But the problem occurs when the position of these, when the configuration of these mines is changed. When you change it, the machine learning algorithm will not work. Now, once again, you'll have to retrain your machine learning algorithm, and now after retraining, only it can work. But the good thing is with the AI algorithms, with the artificial intelligence algorithm, the thing is these algorithms would give us the optimal path from entry to exit, avoiding all these minefields. But at the same time, the AI algorithm would try and learn what these mines are. Okay, so it would learn that it has to avoid these mines. So even if the configuration is changed slightly, the algorithm would know that this is a mine and this has to be avoided. So the AI algorithm can still work. So what we say normally is that the difference between machine learning and AI is that the AI will use the experience, to acquire the knowledge. Whereas the machine learning algorithms, they acquire the learning through experience. So yeah, that's a simple difference between the two. Now let's take an overview of various, AI algorithms. We see, normally I work with the medical robotics, and though we have many other applications, but mostly we work with data that is collected through sensors. And so AI application, if you talk about, it helps us in all these kinds of sensing, comprehending, and acting. So for the sensing, there are a lot of applications of AI. For instance, in computer vision, audio processing, and many others, of course. Comprehending, we've been working in NLP. There's a lot of, these days we work with the self-supervised learning, and we are doing a lot of work there as well in natural language processing, and then in the knowledge presentation and representation. For actuating, again, machine learning expert systems are used for. That's basically for my robotics area, that I deal with different kinds of actuations, and so, for instance, if you talk about some illustrative solutions for sensing, these virtual agents are used for sensing, identifying, virtual agents. We also use in cancer diagnosis, and then of course there's identity analytics, cognitive robotics, speech analytics, such kind of applications. Now there was one study done recently, and it surveyed all the emerging technologies. Where do AI and machine learning stand on the emerging technologies? It was found that, of course, the IoT and the smart sensor technology, they have more adoption in industry and otherwise compared to AI. But once again, the smart sensors and the IoT technology is founded on artificial intelligence. Okay. So in terms of acceptability is at the top, and in terms of applicability, AI algorithms, they are applied in all these sectors, be it transportation, healthcare, water resources, technology, environment, traffic, everywhere. Now, the thing is, this AI, artificial intelligence algorithm that we use now are termed as weak AI. Okay, they are not strong AI. So all we can do is that we can identify data patterns, solve problems, minimize errors in controllers, and of course, working with the genetic evolution, right? We can create algorithms that would learn and evolve over time. But the fact is that the computers cannot think better than humans, and the computers cannot make decisions on their own and work autonomously, and that still remains our goal to achieve. And that is something that we define as a strong AI. If you talk about for the industry, their goal is to achieve finally lights of industries. So what do we mean by lights of industry is that for now we have industries where we've got machines and we've got humans working together. But the goal is to achieve a time where there are no humans working in the industry, and humans are basically doing the job of their thinking. Humans can do planning, thinking, and other kind of execution, whereas the monotonous and routine work can be done with the robots, can be done with the computers, working with the strong AI in lights of industries. So in terms of types of artificial intelligence algorithms, there's a long list. It's such a long list that I cannot cover in this presentation, but to select a few representative ones, I have mentioned them. So basically, or mostly we work with artificial neural network in various of its various forms, of course. Now, second to this artificial neural network comes the genetic evolution that we mostly use. Cellular automata is again quite commonly used. Then we have fuzzy systems, which is also used for control applications other than the predictive capabilities. We use multi-agent system, and mostly the multi-agent system is used where you have multiple customers and vendors. We use swarm intelligence in terms of ant colony behavior, beehive algorithms, and very interesting such kind of algorithms are in place. But let's take one algorithm quickly. We'll try to create a base, and then I'll switch to the application healthcare. So when you talk about neural networks, everyone knows about it. You know, the fundamentals of neural networks are known to most of us now. That we are trying to mimic how our brain works. How our brain works is really complicated, but at least we have been able to understand. We have been able to understand how the basic entity of our human brain, that is the neuron, it works. So in our brain, we got more than 1 billion of these neurons, and they are arranged in a layer formation. So the neurons, they communicate with other neurons. Like, it is estimated that every neuron, it would communicate with at least 10,000 more other neurons. So the neurons to neuron communication happens within the layered structure and also across the layered structure. So as I was telling that the human brain has layers, you know, basically the matter that we have in our human brain is not solid. It's like kind of a fluid, but this fluid has layered structure, and these layers, they have neurons. Neurons talk to each other, and the signal that they talk to each other is electric potential. And so, yeah, if you talk about our human brain, it is the most efficient computer ever constructed. Okay, I mean, our human brain, it consumes like 15 watts of energy and does all the computations which otherwise would be, if you carry out using computers, would cost you 15 million watts. So you can see how efficient is our human brain. And so it is justified if we try to investigate how our brain works, and we try to put that in the circuits. For instance, if we talk about these neuromorphic circuits, where people are trying to learn from the brain and implement everything on electric circuits using those membristors, is a step towards, you know, achieving efficiency, something close to the human brain. But yeah, so what I was talking about, this human brain and the neuron. So neurons, they communicate in terms of electric potential. That's correct. But then there are a bunch of neurons. And bunch of neurons would make it possible for you to learn and process something. For instance, if I ask you how much is 15 times 3 times 2, so your answer would be like 90 maybe. But so how to reach to this answer, you don't have to actually calculate everything. All you need to do is just think, and the answer comes out quickly. So a part of your brain, and that part, there's a small cluster of neurons that is responsible for this multiplication module, has been trained over the time. And so it fires certain potential for different kinds of numbers, and that potential would be converted back in terms of vocal cords, vibrations, and the values that we speak out. Right? Now the entire process happens so quickly that we don't actually realize, but it's a very complicated process. But once again, the kind of potentials developed in my brain may not be the same in someone else's brain. What I mean to say is, if you look at the screen, basically we talk about, okay, so there's a picture of a neuron. neuron would take inputs from the dendrites and would strengthen or weaken those signals into the soma, and that's something we call the weights. So what I was talking about is that while carrying out multiplication, we all have this kind of uh, exchange of potentials in our brain through neurons. But the weights, this weight matrix is different in all of us, right? So if I'm thinking about 15 times 3 times 2 equals to 19, the weight matrix that is working in my brain is different from someone else's. Having said that, what I mean is there can be hundreds of possibilities of these weight matrices and the biases that would create models which are almost accurate, which are accurate of the same order, right? So to repeat once again, what I'm trying to say is that if you are using neural network for modeling, you create a model. What do we mean by creating a model? That we need to identify these parameters and hyperparameters of the neural network. But the set of hyperparameters and parameters that you have identified is not the only solution. There could be multiple sets of hyperparameters and parameters which can be used for modeling and would give you the similar accuracy. And so we don't have a singular solution. There are multiple solutions and multiple neural networks that exist. So this is the basic functioning of neuron. It takes inputs, it would strengthen or weaken the signal depending on its importance. It'll add a bias or subtract a bias. The bias is nothing but simple shifting from the origin that we saw in that straight line equation, y equals to mx plus c. So this m stands for the weight matrix, and the c you also call sometimes it as intercept on y-axis, right? Which is basically bias or the deviation from the origin. And this bias actually has a similar function. So after having done all that, this has to pass through axon. The axon would actually decide whether the output has to be given or not. So these axons basically are those activation functions. I mean, we model these axons in terms of activation functions, and then they further talk to the next neuron. So what's happening in the process is that the input comes to the neuron in the soma through dendrites, which would give them weights, and then this W1 times input 1, W2 times input 2, W3 times input 3, everything put together goes into an activation function. For instance, this sigmoidal activation function is shown here, right? So everything goes into this sigmoidal function, and then the output will come up, which will decide the firing. Okay, so this is one aspect of neural networks, but normally we deal with a lot of inputs and outputs. So in that case, the idea is to come up with a weight matrix that will give us a perfect mapping between inputs and outputs. And to do that, basically we'll have to train our neural network. So what do we mean by training our neural network is identifying those weight matrix, biases, and set of hyperparameters. So what we do is we initialize with the random weights, okay, and then with the random weights, let's say the random weights are giving me some sort of error. For instance, output should have been 0, whereas I'm getting 0.8, so the error is 0.8. I need to now change the weights, to adjust the weights so that the error can be minimized. So we don't actually do this random. It has to go through a certain process. So the changing weight, there are many algorithms once again, which would guide through change in the weights and the biases so that the error can be minimized quickly. So when I say error has to be minimized quickly, yes, I do mean this gradient descent minimization of error Once again, there are many, moment-based, NAG, error grade, error delta, RMS probe, many different kinds of algorithms. Of course, they are all gradient descent algorithms, but they work with different, they work differently with different data. And the objective always remains to minimize the cost function, which is nothing but the error in predicted output and the actual output from the training data. So in doing so, the weights and the biases, they have their own function. They're very important. But at the same time, the activation function, they are also very important. Because the activation function is something that would try to learn the non-linearity in the data. Right? By activation function, what do we mean is, see, once you've calculated this y equals to mx plus c, the entire thing has to go through a function so that the output, appropriate output, can be fired out. Now, what this activation function will do is shown in here. Of course, increasing number of hidden neurons. I mean, to further explain those who are not very conversant with the neural network. So what we have is, we model our neurons in terms of working with we trying to mimic our human brain and trying to come up with, this mathematical model of the human brain. Now, while doing so, what we are trying to do is, the neurons are modeled in terms of activation with an activation function. So the one neuron would mean that it is taking inputs, applying weights, and also converting converting using activation function. Now, so you got, since our human brain works with the layered structure, so here also we use layered structure. Like, we've got an input and output layers, of course, but between inputs and outputs, we also use many hidden layers. So if you use more hidden layers, of course, you get more and more distinction between inputs and outputs. And so the accuracy in identifying the output would be more. That's fine. But as I was telling you, that the weight modification is not done randomly. We use gradient descent algorithm. And so as you can see, when the activation function and the weights are being trained, the discrimination between the inputs and outputs gets finer and finer, and eventually you would come up with such kind of distinction. So here what we're trying to do is minimize error between the predicted values from the model and the actual values that we have in the training data set. And after a certain time, you would see that the distant boundary would clearly differentiate between the two kinds of data. Now, in doing so, as I was telling you, that the activation function also has a very important role. And normally we were working with the sigmoidal, transfer function or the activation function, and we were thinking that the sigmoidal function works very close to the process that goes through our human brain. But over the time, when we started working with the deep learning, I'll also quickly talk about this deep learning later. When we started talking about deep learning, it so happened that having more hidden layers, the gradient that we were calculating while doing backpropagation, it turned out that the gradient would vanish by the time you pass through few of these layers. And so we almost get no signal for calculating the weights, and so the weights are not changing. Okay. So there was a problem. We tried with another, let's say, 10 hyperbolic activation function, and still it has the same problem. Okay. And so these days we normally, of course, working with the artificial neural network, we can still work with We can still use sigmoidal, 10 hyperbolic, or other activation functions, logarithmic or other ones. But the moment we have more than 2 or 3 hidden layers, we definitely have to switch to a different kind of activation function. And nowadays we work with these ReLUs and other activation functions, because the training with these functions, activation functions, is much faster compared to the sigmoidal or the 10 hyperbolic. They are also less expensive as compared to the previous conventional activation functions. Okay, and of course, the problem of vanishing gradient is also not encountered. But of course, this overfitting problem is always encountered. So what happens is, in order to achieve higher and higher accuracies, we sometimes train our networks to a certain extent that the weights and the biases obtained, they will only work with the training data. So if you're talking about the training data, the error is definitely reducing. But the moment you use the test data, after a certain time, the error would start increasing. And so this problem, which we normally term as overfitting, it causes problem because it kind of, I mean, the model that I'm creating should be a generalized model. But if it is overfitting, then the model cannot, the generalization characteristic of model is hampered, and the model cannot be generalized. Of course, you can achieve very high accuracies for the training data, but the moment you use test data, you'll get very strange values, and the error would be enormous. Normally, when I work with my students, I give them an example of backpropagation where they can work with, identifying English alphabets. So this is very interesting. What we normally do is, such kind of, for instance, every alphabet can be defined. Alphabets can be converted to binaries by defining these 7 by 5, that is 35 blocks. So for instance, if I draw letter A here, so by defining these 7 times 5, so I'll get 35 boxes, or 35, you could say, binaries, right? And the positions where I have dark blocks, they are termed as ones, and white blocks are termed as zeros. So any letter can be termed into a 35 binary string. Okay, so as you can see, this letter A has been converted in terms of 35-bit binary. Okay, and similarly, you can also create all other alphabets. Now, I ask my students to train to create first to create a 35 by 16 input matrix, right? So 16 would mean that so 35 by 16 is the input, zeros and ones for the letter, and I'll also have 4 by 16 for the letters target. So for instance, like there are 26 letters in English alphabet, and let's consider only 16 for the beginning. And if so, 16 letters can be defined by a 4-bit binary, and so every letter, for instance, A would be defined as 0, 0, 0, 0, right? And then B could be defined as 0, 0, 0, 1, and so on and so forth. So finally, 1, 1, 1, 1 would become your P, letter P, right? And so they try to work with, and then it's quite interesting that they can identify. I give them any set of binaries, and they can tell me what kind of letters this binary set would make. But the problem comes when the letters are not printed but are handwritten. Right? So when there are handwritten letters and you need to identify these handwritten letters, then it becomes quite difficult, because the input image that I would give to my students would have 28 by 28 grayscale, which would mean that my input size has dimensions of 784, right? And so if you take just one hidden layer with 500 neurons, that would mean that the weight matrix would have 0.4 million weights. And so fitting such kind of a model would be very difficult. So in that case, what we do normally is we create different layers. I mean, there comes the notion of this deep learning. So different layers are responsible to identify different parts of the image. And so when I'm talking about the parts of the image, I'm talking basically at the pixels, edges, contours, objects, object categories, local features, and then I move to the global features. So this is what we normally do, is like having more hidden layers which are responsible for identifying something. Like there could be one layer that identifies vertical lines, another layer would identify horizontal lines. There will be one layer of neurons that would identify small circles in the image. And so having multiple layers to identify different features in an image, and then conclusively combining all the information, finally to predict what kind of letter is this, what kind of alphabet is this, what kind of number is this, okay? And it's because our human brain also works in the layers, so we do the similar thing here. So first, one of the features is identified, and then it goes on in a sequential manner. And so putting together all the layers, finally they conclude with an output. So to understand best, here I have a picture of a person, right? So of course we need to train with so many images, the entire system. I'm just telling you how the system would infer finally when you have a trained system in place. So the entire image would be digitized and would be given to the input layer, where one layer would identify light and dark pixel values. There's a layer which to identify edges. Another layer of hidden layers, hidden neurons, another hidden layer of neurons would identify combination of edges, and there is one layer to identify the different features. And finally, the output layer has to identify combinations of all these features put together to predict that this is the picture of George, or this is the picture of someone X, right? Different kind of. So obviously for the trained neural network, especially the deep learning neural network, this is how it works. So it's just an example to show you how from ANN we try to switch to the deep learning. Okay. Now, working with the deep learning neural networks is not easy again, because as I was telling you that there could be multiple solutions, there could be multiple options for the weights, for the biases, for the activation functions, for the number of neurons, for the number of layers. There's so many things, right? I mean, there are parameters and hyperparameters that you need to decide upon. And so for that, we normally take help of genetic evolution. So what we do here is we create multiple instances of deep learning neural networks. How do you design a neural network? How do you design a deep neural network? Is basically one deep neural network is a set of parameters and hyperparameters. So the moment you change the set of parameters and hyperparameters, it becomes a different model, isn't it? And so we create many such models, and that becomes our initial population. And this initial population is passed through to calculate its fitness. So, for instance, there's a given training data set, and so all these population of neural networks is given a particular training data set to find out which model is giving what kind of errors, right? And so depending on their error values for the same training data set, different neural network models, they are ranked, they are sorted, and they are ranked in terms of their fitnesses. And obviously, those who are giving very high errors would be deleted, and the ones which are giving us less error would be collected, and their copies are once again considered into the same embedding pool, and then we perform those genetic evolutions such as selection, crossover, mutation, and those kind of things. And then the offspring that we come up with, obviously they're expected to be better than their parents. And then this goes on until you find a set of neural networks that has optimal hyperparameters and parameters. So as you can see, input to this genetic evolution were many DNN. By DNN here we mean deep neural networks. So there can be hundreds of such deep neural networks, and these are their initialized hyperparameters encoded. Now over the time, after one cycle of evolution, the hyperparameters encoded would change for each of these DNNs and would become better and better. And so finally, when we end up with when we terminate, we'll have deep neural networks with optimized hyperparameters and the parameters. Now this was all a theoretical overview of AI and machine learning. Let me okay, still 10:30. We still have half an hour to go through the applications part of the AI in healthcare. So first application that we have done is in breast cancer analysis, or rather breast cancer analytics. So what we were trying to come up with is that given the data of a patient, we should be able to predict whether the person would survive for more than 5 years or not. Okay, because it goes very simple. We started working with that, and later we are in the process of making a prognosis tool to help medical doctors in identifying appropriate prognosis of cancer, and then also in identifying appropriate treatment to be given to the patient based on such kind of data analytics. So what we do is, well, to understand and create a model, there are many cancer databases that exist, but the biggest of the cancer database is called SEER data, SEER, SEER database. So in US, they've been collecting information about cancer patients right since 1973, and it's a very rigorous sampling and collection of data. So the SEER data was most suitable database to work with such kind of cancer data analytics. Now the problem is that the cancer data that they collect has many inputs, as many as 200 for every patient. They would have at least 200 types of information, and you need to identify what information is important. And so there we did some sort of dimensionality reduction in order to identify the important information, important data rather, right? On the right hand side, the table shows that important data type and data. So out of 200, 19 18 data types were selected, and the 19th data type, which is survival month, was our output. Now the data that you have is not all numerical data. So most of the times when we work with the medical data, we come across categorical data. Now the categorical data, it's very difficult to handle. For instance, how about a nationality, for instance? Someone's Indian, someone is Pakistani, someone is Malaysian, someone is Korean, someone is Chinese. Now when you deal with such kind of data, and you know, the tools that we have, they normally try to find distance between the data, like how far is 10 from 50, how far is 2 from 6, right? And we can easily find. I mean, of course, with going by the numbers, it's easy to find. But in terms of categorical data, how do you find distance between king and queen, brothers and sisters, George and Matthew? How do you find distance between India and Malaysia? You know, a person's citizenship, for instance, or nationality. So it's very difficult to find the distance between the data when dealing with categorical data. And so we have challenges there to optimizing and minimizing the error, right? And so the categorical data has to be converted to a binary data or a numerical data. And for that, we normally do some sort of data encoding. You might have heard about one-hot encoding and other kinds of, there are many encoding algorithms available. The one which we used during this particular research was neural network-based entity embedding. We did entity embedding for encoding, and it works pretty well when it comes to very vague data. So after this encoding, the entire data is given to, you know, those many instances of deep learning neural network, and through genetic evolution, the parameters and the hyperparameters were evolved and identified, optimized. And then, so you get, let's say you're getting 100 such kind of deep neural networks that gives you very high accuracy and everything's fine. Now, out of these 100 ones, which are all better, you have to select one that works better for your particular application. So such kind of approach, it helps in transfer learning, and it also helps in meta learning. So those who are working in the fields of transfer learning and meta learning, they should look at this particular paper that I'm talking about. So we did this and were able to, you know, make good predictions, as is seen in here on the screen. So given a patient data, we are able to predict the survival month for the patient, and works pretty well. So normally when it comes to the image processing, we work with convolutional neural network. In the convolutional neural network, again, the problem is that when you have affine transformations, like these convolutional neural networks, they are fine. They're quite robust for linear translation kind of a transformation. But when it comes to the rotation or shading or scaling kind of transformation, the CNN cannot work. And so we have done some work here to make CNN robust to the rotation and shear kind of transformation as well. So the first thing that we did was, of course, when we have new researchers coming to us working in AI, the first thing we did for the first task that I would give to my student would be to do this face and object detection. And as you can see, even with the mask, the algorithm is able to identify this person's name as Sungat. And well, we have such names in Senegalicia, so don't worry about that. one more example of face and object detection. So we are trying to identify name of the people, the safety gear that they have all put on. So the safety vest, helmet, goggles, mask, everything can be detected. We also done some work on face and temperature detection. So what happens, like our face temperature is always slightly higher, 2 degrees higher than our body temperature. And so it was really, I mean, this research was carried out in 2018 and 19, but with this recent pandemic of COVID-19, it helped us, applying this and making it popular. So one of our system has been installed in a particular mall where we simply by processing the image were able to identify the face temperature of the body. There's another kind of application of convolutional neural network that we've done is in identifying a person through his walk. The way a person walks is the signature of person's identity. And there again, we create a gate energy image using the frames, and then gate energy image is created, and so we are able to tell the person's name by simply with these CCTVs. The other thing was the automatic description of video content. So you take a video and input this video file to the algorithm, and the algorithm would tell us what actually is happening there. Okay, so for instance, here a woman is cooking in the kitchen, right? So the actual caption was the woman is cooking in the kitchen, and the model also gave us the same output as the woman is cooking in the kitchen. For instance, there was a caption, a little kid playing in the bathtub with his toys, and our model output was that a person is playing with a toy, which is quite same. There's another one was like, here we tried to fail our model. So what we did is, we had an animated red car. I mean, it was all animation, but the model says that a man is driving a car. So that was something we tried to, yeah. Now, we do have a healthcare robotics lab, and we work with the assistive and rehabilitation robots, prosthetics. We do work with surgical robots. I'll quickly go through all this and tell you what we do. So the problem that we work with is a disability that normally people have after they receive these neurological disorders. So a person maybe because of injury or maybe because of some neurological disorders become disabled. And to your surprise, one third of the world's population at some or other point in their life would need some sort of rehabilitation. And so what we do is we create, otherwise going through a physiotherapist, how you do is like you visit a physiotherapist and the physiotherapist would move your limbs, hand or legs, whatever, by hands and get involved with you. But we have created robots that would make the person move. Now, making robots is not as great as controlling and using AI. So using artificial intelligence, what we do is we create the controller. Now, the controller, now you must be wondering what kind of application of this AI that I'm talking about in the controller. So what we do is the robot has to move the leg, right? And so the controller has to move the robot and also leg which is attached to the robot. So the controller has to give sufficient inputs to the motors so that leg and exoskeleton, or the leg and the robot together can be moved. So for that, I need to understand my system, which consists of the robot and the human leg. And understanding human leg is very difficult because I should know what happens at hip, knee, and the ankle joint. I should know what are the muscles, what are the tendons, what are the ligaments, and other soft tissues, how they're working. So all these have to be, I need to create mathematical models for all these and put them together, couple them together to create one dynamic model. That will be the dynamic model, the human leg would be coupled with the dynamic model, the robot, and then I can control. Then only I can design a controller for this. The other kind of application of AI, artificial intelligence and machine learning that I have in these kind of robotics is performing the cognitive rehabilitation. So what happens is, while the robot is moving person's limbs, so what we do is a person would come to us in a wheelchair, and then our machine will lift this person from the wheelchair and will place him on the treadmill where he can walk with the help of the robot. Now, while the person is walking, we also make this person, we use this HoloLens from Microsoft. The HoloLens is a mixed reality device where you can see, the person is able to see his treadmill and everything, but can also see a forest where he's walking in. So we make this patient play some sort of games like treasure hunt or climbing up and climbing down, and so the person is also playing games while walking with the robots. Now the type of the game has to be changed with the type of human capabilities, and that's where we use a lot of artificial intelligence. We did many such kind of robot designs, and so the entire platform that we create has personalized program games. There we use a lot of AI. We do use brain-computer interface where we use AI again to understand the brain signal and act accordingly. A surgical robot that I'm currently working on will be able to do the fracture reduction. So when there's a fracture, or when the bone is fractured, right? Because you have muscles pulling the bones all around. So as soon as the bone is fractured, the bone would go into each other like this. So both the fractured parts of the bone will have to be pulled up and then oriented. Normally we use traction table to do that, but with the help of a robotic system that you can see in the figure here down there, it can be done with more accuracies and without pain. So normally in the fracture reduction, what we have is we do physical examination, take X-rays, CT scan, MRI, bone scan. These are the procedures that are done for the fracture examination. And there are pre-operative procedures where we try to classify what kind of fracture is this, how are we going to do it, and what should be the device treatment plan. And then we do this while performing the operations. We make decisions on open reduction, closed reduction, and there's a fluoroscopy done that has to be navigated all through. And so there again, we have created such kind of a robotic system that I was showing you. Wait, this is the robotic system as seen here. And so it is a 6 degree of freedom parallel robotic system using AI and machine learning. It is being controlled and taken over. So then these are the initial results that we're getting from. And so they're very encouraging actually. So both the traction and the orientation of the fracture bone that we call fracture reduction, the entire process is done very efficiently and with more enhanced accuracies. So yeah, with this probably I'll stop here. While we do research, we also have some startups. I've got 2 startups companies funded with the World Bank grants, and so we are working fine with them. I think I can take. I should stop sharing first. Yeah. So I stopped sharing my screen now. And I think we still have some time for the questions, at least 10 minutes.
Thank you so much, sir. Really, session is very wonderful and very informative. I hope our participants get benefit for the session. Now, participants, if you have any query, you can unmute yourself. Sir, currently we are working on a this last slide you have shown the fracture sensor. So, what type of sensors you use, sir?
Yeah. So what we do basically is, see, normally fluoroscopy is done, and what happens basically, the patient, doctors, and the other stuff, they're exposed to radiations. And here's something. Okay. So we are trying to minimize that radiation exposure. And so there we use cameras, and with the help of the cameras, what we do is we don't take X-ray images, right? That is only taken once, and then we do 3D construction, 3D reconstruction of these images. So X-ray images are reconstructed to create a 3D model, and then we have a generalized musculoskeletal model of the leg. See here, I'm talking about the femur bone reduction. So I know I have this musculoskeletal model which I can scale up or down, or maybe I can attune it to a particular subject. So with the help of these two, we try to find the optimal way of traction and the orientation. So as I was telling, that after the fracture, the bones would go into each other. So the parts of the bone, they need to be pulled out and also to be rotated. Now, in pulling out and rotating, we need to make sure that the soft tissues are not broken, they are not damaged, right? And so we have another path optimization module that would tell us what should be the path trajectory of pulling and orientation, so that the soft tissues are not damaged. So still in the very beginning of very infant stage of research, but we are at least able to control it with high accuracy using flexible actuators. Now, working with the actual patient would be the future task, because this is the research project that I'm working on, and the project started from January 2022. Actually, it's a 3-year long project. By the end of the project, we expect to come up with a device that we will be able to commercialize again. Like I'm working with other previous rehabilitation robots.
Thank you, sir. Any other query from participant side?
So is this is today the last day for the workshop, or?
Yes, sir. Today is the last day.
So I wish you all the best for this, and you've been doing a great job, because I think this is consecutively second or third such kind of workshop, isn't it?
Yes, sir.
So yeah, I wish you all the best.
Thank you so much.
Thank you. Thank you so much, sir.
Yeah, thank you. Thank you, Dr. Pooja.
Now, yes, thank you, sir. Now, all participants are requested to turn on your camera for a group photograph.